Hello, welcome to another video. Today I'm taking a look at some old computer circuit boards that have failed batteries and they've started to leak. And this is a really common occurrence that happens on a lot of computers, so the reason to make this video is to look at a possible alternative to these components. One of the things I've looked at for a little while is supercapacitors and their ability to do, low energy storage type application. And so we're going to take a look at these two boards. First one's old clock card from a PCAT, and it's pretty well wrecked, but it still has continuity, so I think we can save this one. And the other one's actually in okay conditions. It just started to leak. It's a 386 motherboard, so I think we can save this one. Let's get into it. Let's go ahead and measure how much resistance there is across this one. Basically don't measure anything, because these are supposed to draw extremely tiny amounts of current so that they last a long time. Let's go ahead and put this in diode mode, see if we measure even a diode drop. Nothing. So this one's promising for repair. Okay, so some repair work has been done. You can see I got some mustard and ketchup wires stuck onto each one of these boards as part of our repair process here. And so right now we're hooked up to this little board right here with power supply, supplying a voltage. We're actually measuring the real voltage here, actually on across the board effectively. There's almost no current, so the voltage drop is going to be 0 across this little short lead, and it's the output on this side that we're measuring. So what we have here is about 3.6 volts, which is the nominal battery voltage, and we have about 20.6 microamps going into this board right now to maintain the basically maintain oscillation, keep that clock ticking, so to speak. I'm going to go ahead and turn the voltage down a little, and we'll see how that changes as it drops. So let's go down. So 3.2, or about 14, 3 volts, 12, about 2 volts, 3 microamps. I have no idea if it's still working at this point. I'm not going to consider 2 volts to be a intolerance rating on a 3.6 volt battery. We can go with a nominal value, say about 3.2 volts, and say about 15 microamps. That gives us a good target to work from. So that's this one. Okay, so on this board we're actually switched down to another range on here. We're actually measuring in nanoamps. So this board is obviously a lot newer technology, and you can see that the real-time clock basically doesn't use anything to stay operational and keep your CMOS backup. So here we have our positive wire going into our board. You can't see that, it's just off camera here. And it's coming back out. Same setup on the other board. I'm going to add our 3.6 volts, and you can see we're using about 30 nanoamps. Basically nothing. I mean, if we have any kind of voltage regulator or something to maintain a steady voltage on this, it's going to use more power than this board itself is going to use. So this thing's basically not consuming any power to maintain settings, which is great. This is going to be a really easy one to repair. Oh yeah, it's back. The whiteboard. So now we got to design a circuit. You'll notice on those boards I ran our red wire, which is our 5 volt line, on both boards. That means we have a 5 volt supply we can work with. So what is our goal here? We need to take this 5 volts, we need to have some kind of storage, and then we need to supply some kind of regulated voltage back to the board. So we need, approximately 3.6 volts. So that seems pretty simple, and what's used in a lot of devices these days for doing this task is supercapacitors, or electric double layer capacitors. You can look up a whole bunch of information about them on the internet, but for the most part they come in 2.7 volt variants. There's a few 3 volt and things like that out there, but you can stack them 2 in series and not have to worry too much about balancing, especially in really low current circuits. So that's what we're going to do here. So first thing we're going to do is we're going to take that 5 volt rail, we're going to go through a diode, probably Schottky, go through some kind of resistor, and then we're going to charge those capacitors, which is going to be 2 capacitors in series, and this is going to connect to the 0 volt rail. So that's basically our charging circuit. Got to figure out what value we want there. Hope we don't lose too much resistance here, and then we have to do some kind of regulation on the output side of that. Simplest way to do that is probably just use a dropping transistor and a resistor and some kind of diode, probably 2 diodes, probably LEDs. And then maybe put a small capacitor on the output. And that's going to be our regulated output. That's pretty much it. So whatever value we tune these diodes to, and this resistor, so the resistor is going to set the current that will be able to flow through this. And we know we don't need basically any current for either of these devices, so this could be a very high value, so we have very little loss through here. So our quiescent current is going to be, in the order of a couple microamps, and then our regulation is going to happen by basically how stable these diodes are. So if they're not perfect, it doesn't really matter. This thing's a battery, so I don't see why our regulation is going to be really all that important. This is just, the clock circuit, so it's logic signals, so it's 1 or 0. So a little bit of noise on this circuit's not going to make any difference. And this is about the cheapest, simplest thing I could think of to do this. So to keep this path as low current as possible, we're going to use a pretty high gain transistor here. So I think that's the circuit. We can do some math on this over here. If we have a, what do we want, 0.1 amps, and we're going to be starting at 0 volts across these capacitors, 100 milliamps, 5 divided by 0.1 is 50 ohms, and 51 is a standard ohm value, so we'll put a 51 ohm resistor there, and that's going to be about half a watt, so that needs to be a 0.5 watt resistor. And then these values are going to be X number of farads. So these are actually going to be multi-farad capacitors to be able to store the energy for a longer amount of time. So that's the circuit. Let's go ahead and we'll put this in a SPICE simulator, figure out what some of these values need to be to get this thing to work, and then we'll build it up on a breadboard real quick, just make sure it functions the way we expect and there's not too much in terms of variables. Then we'll build up a couple circuits and install them and see if they work. All right, back again. And we pretty much followed exactly the parameters. The only thing we custom tuned was these little regulator, the actual diodes, which are using 2 LEDs. And you can see we're right at 3.6 volts. Right now we have a 9 meg ohm load across it. So we're going to take that out. You can see it stays just about at 3.6 volts. So that's really good. That was actually 9.1 meg. So this is actually a 100K ohm load. You can see we have a little bit of voltage sag. So now we're about 3.49. Great. That's perfectly fine. We can go a little lower. Let's see. It should start to drop off. Take it down to like 30K. That's still great. So yeah, I'm good with that. So I think this circuit's good, and this, oh, it's 0 ohms. Probably doesn't like that, right? Let's see what that does. 0. Yeah, okay. Yeah, it takes short circuits. There's a short circuit. So it is short circuit tolerant. Hey. So now the supercapacitors are in circuit and are being charged. So you can see the voltage is really low now, but we still have 5 volts over here. But now you can see we're drawing some current on our power supply. So this is going to take a little while to charge because we're going through that 51 ohm resistor. So this will basically sit here for a little while, and I'll be back when we get to some stable voltages. So here we can see the basic calculations for this device. We have an input voltage of 5 volts. We know we have a resistance that we're charging through. We have a storage capacitor size. We have an output voltage goal. We have an output current. And we have a resistor we're charging through. There are several factors to consider for how the power gets used on the other side. So we have the output power that's actually being used to maintain our battery. We have quiescent power, so this is just used to regulate the output voltage. And then we have reverse diode leakage, which is actually our worst culprit in this case because this is not a great circuit. This is just a proof of concept. So what we find here is with this current setup with 4 microamps of reverse diode leakage and about a 2 microamp output current, we have about 11 days of hold up time with the 12.5 farad of capacitance. And this is across 2 capacitors. This isn't great, but again, this is a proof of concept circuit. We could actually improve this a little bit, but for what I want to do is probably mess around with one of these 386s for a couple days and then probably put it away for a year. It's really good enough for me, just to maintain the settings for a couple of days, and then I'm done with it. We can improve this to get much, much larger times here, but for now, this is okay. This number here has a huge effect on the overall results. So we can see if we turn this to 0, we get about 23 days out of this exact same system. And if we lower this to 0.5, which is probably a more realistic value, or even lower than that, modern systems are going to use something more like 0.1 microamps. So 100 nanoamps to maintain the clock. We can see that hold up time increases to 38 days just by changing those couple of numbers around. Now, of course, this circuit would never do that because it doesn't have, it has that reverse leakage that's very significant. So it just, it's not off, right? So I'm going with 11 days, and this is in line with what I got for a simulation. So I'm going to pull that up now. So here's the circuit itself that we're actually using. So we have a diode, a resistor, and our capacitor. I'm showing a 4 farad capacitor here. So this is only 200,000 seconds, but in reality, the one I used was 12.5 farads total. We have a 510K resistor into our transistor and a couple of LEDs we're actually using for our voltage regulator, essentially. And then a small output capacitor isn't really needed, but it's there just for smoothing. And then our output load resistor. So our output voltage stays basically constant while our voltage across our capacitor falls over time. And you can see this is a charge period right here. So a few seconds of charge brings us back up to our charge voltage and then falls over time. So a few minutes of on time, lots of time off will maintain the voltage for this system. Again, this is not the best circuit. It's not, doesn't have any regulation on this capacitor right here. So if you put too much voltage in here, it will overcharge this capacitor. It's also not a constant current circuit, so it takes longer to charge. This resistor doesn't change its value anytime. So as this gets more full, this presents less of a load. So effectively this becomes a higher, if you want to look at it as a resistor divider, effectively becomes a higher and higher value resistor, which means it charges slower and slower and slower. Okay, well, we're back and the thing's all charged up. I actually kind of walked away for a while, so I didn't see exactly how long it took, but I do have the calculation, so we know roughly what it took. I can see this charge up to about 4.71. So of the 5 volts that were on the rail, we lost about 0.3 volts. That was expected because we're using the Schottky diode. And then we're regulating down to 3.444 for our output. Right now we're going into a 100k ohm load, so for something like this, that's actually pretty aggressive. Yeah, so that's it. I think this circuit works pretty good. I'm going to go ahead and build up a couple of these and get them installed on these cards and to see if they can maintain their BIOS settings through a couple power cycles. All right, well, so we built a couple of these little modules and got one charging up on our 386 and see how long it lasts. This little clock card here for an old PCAT should be able to keep the time now. Yeah, so a couple supercapacitors, a little regulator circuit over here. We'll see how they work throughout time. I'll make an update video at some point in the future, but for now they seem to be working good. All right, thanks for watching. Like and subscribe.